Okay, Martin, you can probably get going now.
Okay. Yeah, I'll get started. Yeah, with this one, I probably need a lot of help here, but I have some it's a little bit confused with some things. But yeah, one of um, the 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 main um, the main idea of here on this part, second half of this is basically bits back coding. That's where most of the focus is. There are two separate ones: the continuous ones, and then the Lampel Ziff ones. But all the rest are, are based on bits back coding. One of the things that's kind of confusing is, at least for me, is when we're in discrete space, when we're in continuous space, it's all supposed to be lossless, but seems like it, sometimes the notation is a little bit confusing, but hopefully we can work through all of that. Okay, so let's just go in. So this is just a refresher on the on information theory. So entropy is the probability of the log 1 over p of xi, the entropy, and this is the lower bound on the number of bits we can use for each symbol. If each symbol is p of xi, and then yeah, and then if it's a zero order Markov model, then any compression scheme must use greater than or equal to h of x bits per symbol on average. And so the bits can be doesn't have to be integer. It can be any real number. So it could be 0.5 bits or anything like that. And Huffman Huffman coding uses Huffman codes uses at most h of x plus 1 bits per symbol. So the lower bound was h of x. The entropy, you cannot use less bits per symbol, but then that symbol, you cannot use less than h of x bits per symbol on average. And Huffman code showed that there was a practical one where you could do h of x plus 1 bits per symbol. And so this is an actual code, but this is a theoretical limit from Shannon. And then the other one was that we looked at last time was arithmetic coding. And this is very close to the entropy. There's only a +2, but this +1 is on per symbol, and it's the upper bound. This +2 is on the entire message. Right, so that was stuff we looked at last time. Okay. So in order to do all the stuff that we did previously, we have to make some assumptions. The Huffman encoding assumes that you can tractably enumerate all of x, that there's a finite symbol, and then you can assign probability to each and every one of them. And then arithmetic coding says something similar, that you can assign interval to each x up, and interval matches up to the probability. For each of the messages. Okay, so some small number of values x can take on. Okay, when are these violated? So there's two ways where they're violated. When x is continuous, when x is continuous, obviously the can be enumerated and can't assign an interval. when X is high dimensional. And so here in high dimensional, we can, okay, okay, these are the two ones. The when it's continuous and it's high dimensional. Okay, let's look at how to deal with continuous ones. So with continuous, you do discretization with some precision t, and then we can discretize in the x domain or the cumulative domain. So we, suppose if it's a normal distribution, we can either say we cut up the x domain into smaller precision values, or the cumulative one. I should the but he shows the picture here. I should have kept the but yeah, so you can cut it up on the x domain, or you can do it in the y domain when you do the CDF. But there are the two options. But the question still remains: if you discretize it, can it, can we still can it still be lossless? What happens? You use all these coding, but I think it's so here the x is the actual data that's coming. So if you if it's continuous, then there's no way to do actually lossless. But if you have probability, then that's fine. You don't have to worry about that. We can still do lossless because so this whole yeah, so this whole thing it's a little bit like I don't know when you would even have this, when you would have x as continuous and you need to compress it. Because if it's images or text or anything, it's always discrete. But anyway, there's this there's this bit of confusing formula here, which is not used in the future. So, but the H, which I guess is some sort of entropy of it, and so the discretization with some precision t. So I don't know what that precision t actually means. If we assume, let's say, it's the size of the intervals. Let's just assume that is the case. Then if this is just the formula for the entropy here, TP xi log TP of xi. And if you separate the log parts out, because log T of pxi is log T of I'm sorry, yeah. So log T of pxi is T time, log T plus log P of xi. So then TP of xi log T is here, and then T of pxi log pxi. So they kind of switched it up. It's the other way around, but see the T goes here, and then the pxi goes over here. And this turns out to be the continuous version of the so this is almost equal to the continuous version of the entropy, which is called the differential entropy. And then it subtracts log of t, because integral of x over p of x is 1, because the probability sums to 1. So we have log of t. And it says matches intuition, making t smaller results in more buckets. So as t goes to 0, log of t is precision. As the precision or the discretization intervals goes to 0, the entropy goes to infinity. But yeah, at some point, if t is 1, then the differential entropy matches the actual entropy. So it kind of, I don't know what what exactly this is, but anyway, but we also, but if we have a continuous domain, we can just truncate it, and we get some sort of um, some way to use Huffman coding and arithmetic coding and get the answer. As you know, there's nothing um, strange. I mean, nothing revelationary. It's just the standard way of doing things. Okay, but I don't think we'll use this again. So I'm not sure why it's here. Okay. So let's look at the other case where p of x, where x is high dimensional. So and so if x is normally distributed, then each the way to deal with it is either use an autoregressive model, or where each dimension is dependent on the other ones, or each dimension as independent random variables. And so you'd code each random variable um, efficiently and then combine them together into a bigger one. Or if there's interdependence, I guess you can use an autoregressive model. So if you think of image as the first one, as each pixel dependent on the next one, you can think of it as being something very high dimensional. So then we use the autoregressive model, right? So to do that, or we could treat it independently and then just encode each pixel separately. Okay, and so let's so those were the two how to deal with them. So I don't think we'll get back to come back to those two in the rest of the lecture. Okay, so mixture models. So mixture models is this is the we've dealt with these mixture models quite a bit. So a mixture of, so example is a mixture of Gaussians. So you just have a whole bunch of Gaussians, and that gives you a better Gaussian than just one. I think there's a picture that was drawn here. Yep. Okay. So here you have three Gaussians, and it is more complicated than the single Gaussian, right? So, so yeah. So here's the question. So this is the question that they ask, and if if Px is a mixture model of easily encodable distributions, can we efficiently encode P of x? So our data comes from a mixture model of easily encodable distributions. Um, how do we encode it efficiently? Um, yeah, so that is the main question. I mean, for if sorry, if the probability is a mixture model, probability of x is a mixture model, if x is still is still a discrete, x is still discrete, and then the probability is a mixture of models. How do we encode it efficiently so that so that we minimize the we maximize the compression, right? So that's the main question here. Okay, so here's the running example, and this was the diagram for it. So okay, so P of I is the probability of the model, and then probability of x given I. And so this will give you the total probability of x. So here in this case, there's this is the probability of x dependent on I, which is for three different distributions. And so if we choose, I think this is what it means down here. If we choose P of xi with a specific I to code for x, then the cost will be log of 1 over P of xi. So we're only using one distribution to code for it instead of doing the entire one. So this will be the cost. So instead of having this entire distribution, we just say, well, we have these three distributions and we know where they are. And if we use this guy, let's say number 1, to code for x, this would be the cost of encoding x. X. Okay, so before we go into bitback coding, there's a couple of motivation techniques that we go through. Okay, so we're back to I mean, we start off with the one that we've been looking at, the mixture model. So here, so we look at all of these i's and find the one that maximizes pi of x. And so okay, so if x is somewhere here, I think there's a illustration here by Peter. Yeah, and so if x is here, then 3 maximizes it, so we use 3 to encode it. And the question is it optimal? No, because we're using different distributions. It doesn't have to be, right? So this is the actual distribution here on the left, and this is the distribution we're coding with. So this is the actual one. This is what we're coding because it will flip from one to the other depending on which one is the max. And so if we look at the code length, it's the probability of x, yeah, min log I pi of x, the one that gives us the minimum. And j is, I don't know what j is. The second part is. Yeah, and so the cost is the entropy plus the KL divergence. And so the KL divergence, especially around here, will have some KL divergence because we're using this to encode this value here of x to encode, but the actual value is up here. Probability is much higher. So this is not optimal, but that's one way of doing it, is that we just say we send I, we're saying which distribution we're using to the decoder, and then we send x, the value of x, depending on the distribution. Okay, so this is max mode coding. So then the second motivation, this is before we get to bits back coding, is called posterior sampling coding. So we still have the same setup here. P of I, mixture models, Pi, Px given I. Only difference here is in the previous one, we did maximize Pi of x. Here we just sample one of them. Just take any one. You know, you can just randomly sample one. And so we have to send I, and then we have to send x, just like the last time. And so here's the expected code length, which is almost similar to the previous one, but it doesn't have the min I. It is just the regular one. Okay, and then so it's optimal, yes and no. This one is also yes and no. If they're separate, it should be yes, but yeah. And so this is yes and no if we'd like to send um, yeah, and this is more expensive because we're not using the max, so it will take more bits. There'll be more divergence from the the full distribution, right? So that's what because we're not choosing the best one, we're just choosing one. So this leads to bit spec coding. So that's like the main thing of this, and so this is pretty confusing. So hopefully I can uh, get some idea of it. So it's the same thing here. So sample I, same as the previous one, posterior sampling. So you just sample I from pi of x, send I, and send x, right? Um, but where's the bits back coming from? The bits back comes from that when the receiver receives the message, it can decode I and X, right? I and X. Um, Plus, it knows Pi of X because that is shared between the models. But what is different here is that it can also figure out how you sampled I. So you can reconstruct the random bits used to sample Pi of X. So what essentially we're doing is we're using some information to sample Pi of X. So we're not randomly, even though we're randomly choosing Pi, we could actually be choosing it from some information beforehand. So so if there were 10 distributions and we chose the fourth one, then the decoder knows you chose the fourth one. So there's some information being transmitted that way, right? Um, so the actual strategy of sampling, which one we sampled, actually conveys information. And so that's the idea that you are getting the bits back because the sampling itself can be done with information. So instead of using randomized, you use it with some information because you use it with some information. But when you sample it with that information, the decoder can reconstruct the random bits used to sample and can figure out, okay, that's how you sampled it. That's why you chose this I. And so that's extra information that you just transmitted over. So it's just like the previous one, except that now that the decoder has um, knows about it. So I guess previously we just sampled and we didn't say how we sampled I, but here we'll say we sample I from some bit string or some strategy, that is dictated, and that information is then transmitted to the receiver. Okay, and so there's so those random bits are also sent, and um, the information that is sent is log 1 over pi of x because we chose I of x. Then That's bits we got. So we can do the formula here. So log p 1 over pi, that's for this one, send I. So this is for sending the I. So which one we chose, and this is for the encoding of x given I. So encoding x given the distribution of I. And this one that the bits back that we got from actual sampling, which is log 1 over pi of x. And if we work through this, um, these are all logs, right? So you can just turn them into a big fraction. So this is what it's been done. It's this big fraction. So pi of x is pi, into I comma x divided by p of x, and pxi is pix divided by p of I. And this p of I, this p of I cancels, and there's only this p of x left at the bottom. So it actually becomes log 1 of p of x. And turns out this is an optimal code, because a log of px would make it optimal. Is that, I know it's very non-intuitive in that there's some bits being hidden here, transmitting here by the actual sampling of it. But apparently somehow it works out to be optimal. So that's like the basic idea of bit spec coding. Um, okay, so this, I'm not sure what this picture is. What I okay. So symbol data, auxiliary data, and then the sender can get the symbol data and the auxiliary data out. So so I guess the auxiliary data is the one that is used as the random bit string to do the sampling. So you could transmit some extra data along with your symbol data um, to the receiver. But as we'll see, I think they do something called chaining. Um, yeah, they do something called chaining. So here's the paper that well, this is a paper for bitspec coding, but it's a newer version of it. But um, they do say it works pretty well. So trying to compress the binarized MNIST, PNG, BZ2, and BBANS is the bitspec symmetric numeral system. This is the one that we'll look at in some more detail. The ANS is a replacement, or I mean, a different version of arithmetic coding. But this is the bitspec, so it works pretty well. And yeah, but this whole paper is based on using it as a VAE, where there's a symbol, and then the symbol is dictated by a latent variable. But here we have a mixture model, so it's yeah, it's slightly different use case here. Um, okay, and so this slide with approximate inference. In the previous slide, we knew the exact PI, but if we're trying to use it with a VAE, then we just have an approximate way of approximation, right? So we don't know what P of I is. We only have Q of I given X. Um, because before we assumed that we knew P of X given I and Q of P of I given X, but we don't know P of I given X, so we have to approximate it. And this works out very well in the VAE case, where we're using latent variables to figure this out. So if we're given x, what is the latent variable, right? So that's something that we have to figure out. And then yeah, these two are the same. The probability of I and then the probability of x given I. Okay, and then I think the only difference here is so recipient decodes I and x and then knows the qi of x. So you can reconstruct the random bits just like we did before. Okay, and then it's the same thing, you know, the log 1 over qi of x random bits were sent. But the only difference here is that this fraction here, I'll go back to the derivation here before. Right here, we simplified it to log 1 over p of x, but this p is now a q, right? So this becomes 1 over p of I, 1 over p of xi, and 1 over qi of x. And this is equal to the elbow in the VAE. It turns out that this is equal to the elbow. So it's one of the intermediate versions of it, right? So we start with 1 over prob in the elbow derivation. It's one of the intermediate steps. But since we use elbow for as our function, loss function, so training the VAE and optimizing the compression is the same problem. Turns out it's the same problem. So if we optimize the VAE, it also does very well with the coding. So we don't have, so that saves a lot of problems. That you can use the same loss function, and then whatever you get, it's the best for compression. Okay, and so this, let's go back to the bits back again. And so now we do have the BBANS here, but we'll talk about how ANS works a little bit later. It's in the second part of the lecture. So the way it works is we have some information. We start out with some information. So the first step is you take a little bit of the information, snip out a little bit of information, and use it to sample. And that amount is log Q. So here we have to use a slightly different notation. So Y is the latent variable, and S is the actual data. So S starts with a symbol, and then Y is the latent. So instead of X and Z, we have to think of S and Y. So that's again a switch from the X and I and X and Z that we used before. So just S is the symbol, S stands for symbol. This is the one that we're encoding that we see, and Y is the latent variable or latent representation. Okay, so we use up a little bit of the bits to sample. So then that usage gives us the distribution to use. So here Y naught is the latent variable representation given the symbol S naught that we're trying to encode. So our information goes backwards first, and then we encode the we encode the symbol S naught given Y naught, and so that increases the size of the message, and then we encode which one we used, which latent variable or latent distribution we use. So those are we encode it in the stack. So that's the one loop, and I think, and then this below part becomes the top part, and then you can go backwards and then 2-step forwards. For the first step, you can use either random information or you can use some other like metadata or something like that. You can just put it in there to get the process started. But then you can always put these. You can always use the previous one to encode the last one. So yeah, it has a consequence that you have to decode backwards, but yeah. But that's the basic idea of bits back. And then I think they call it chaining here. So chaining bits back. And this is the exact diagram. So you just do this and you chain it over and over and again until you get to the end of the message, right? So okay. So how do we actually get these bits back? Oh, sorry. We have use random bits to generate I. How exactly can this work mechanically? Okay, so yeah, this seems out of place, but okay, and this is the history of it, and can skip over this. I think this is the paper that I was looking at. That's over here, the bits back with ANS, but it was back to the Hinton Wallace 1993 time. And this is the bit swap, and these are the two papers that Peter Beal's group have written. Okay, and so the next one is the symmetrical ANS system that we can use instead of arithmetic coding. Okay, so this is a simple this is a different encoding algorithm. It's not related. It's a symbol encoding algorithm, just like arithmetic coding or Huff encoding. So it's just a coding system. So the high level idea is, yeah, use natural numbers as encodings. The longer the symbol sequence, the higher the natural number becomes. In arithmetic coding, it was just find a number between 0 and 1, or find an interval between 0 and 1. But here it's find a natural number. So here's an example. If probability of A is 1/4 and probability of B is 3/4, the encoding is so okay, 1/4 of the natural number should correspond to a sequence ending in A, and 3/4 should corresponding to ending in B. So the idea is, if we start, if the first letter is A, then the number is 0. And the first letter is B, then it becomes 1. And so if then now becomes, if it's going to be BB, so if the previous numbers was 1 and a B came, then it becomes 2. If the previous number was 1 and then an A comes, it becomes 4. And so you have to look at 4 and B, and then it becomes 6. Right. So the idea here is that if you have, I think the example was ABA. Let's see if I can get to that somewhere here. BAB. So 0B becomes 1, 1A becomes 4, 4B becomes 6 from the lookup table. And so you have a integer representation of the code as a big integer. And so yeah, and so this is the basic idea, and then he emphasizes that it's almost like a stack, because you decode from the backwards. So you always say what was the last number here? It was, if it's 6, then you know it's a B, right? If you know it's 6, then it was B, and then you can say, okay, what was the one before it? Then you say, okay, 4. 4 means that it was an A, and so you kind of decode backwards from there. Um, okay, and did we talk about this? Okay, yeah. Okay, so I don't remember this part, but we'll just go to this one. So this is the paper that I was looking at, and so they combine bits back and ANS together in this paper. So the idea here is that we have the VAE model. So you have PX. This is the standard P the VAE model, right? The Z. So we're back to X and Z instead of Y and S. And then this is the bits back phase. Decode or sample some latent variable from the from an auxiliary source, or use some previous data to sample the latent variable, and then from that latent variable you get a distribution, and then from that encode X, and then encode the Z that you used. And so the code length is this part. I'm not sure why this is the case. This is probably the addition of these two. Yeah, so this would be probably the X given Z and probably the Z, so it becomes probably of X and Z, and this is from the other value. Oh. So this is just a standard ANS. Okay, and here's the illustration of it. Here's the bit stream. You use it up to decode Z, and that decoding Z, finding the latent variable, you can use it to encode X and then encode Z, and then the receiver figures out has the stack version of it, and so it decodes Z, decodes X, and then it can figure out what Z was. The word encode is used here, but yeah, it's just a little bit confusing here. It's like decode, encode, encode, but decode, decode, encode, but it's basically figuring out what all of these were, and so it can put it back onto the stream. And it's slowly so when it decodes, it removes this part. When it decodes this, it removes this part. When it does it, and it puts something back, and then it's eating up the stream backwards. Okay, so these are the assumptions that we have to look at. So finite precision approximation of log 1 over p, inefficiency in coding the first data point. So the first data point always has some random stuff that you have to put in there. So it has to be amortized, or you just use some metadata that you'd have to store anyway. So VAE has continuous latent variables, so that has to be dealt with because the Z is continuous, and the need for clean bits. The fear is always that when you use these bits from the we generate this message, and then we use the this last portion for the random bits for the next iteration, right? So it ends up being like dirty bit, could not be might be not clean, so it might not be fully random. That might cause problems. So it says, see next slide. So so we discretize it, and we discretize it. Discretize the continuous distribution of P, and then we discretize Z also. So that's the solution to it. And I expect that it should be fine because we'll still have lossless output for X, even though we discretize Z. And so the expected encoding length is this one. Yeah, this is some weird notation with delta Z that it cancels out. So and it's probably some discretization level thing that they talked about here. But so the cost of all this discretization they say it's just the KL divergence between the continuous and discrete approximation, and should go down with delta Z, or shouldn't. We can probably bound it, so it should not explode. Okay, and then the question: are the bits clean? So in the paper they say it works pretty well. This is the same figure as before. We're sampling from Q Z given X. So X is our data, Z is our latent variables. And the question is our random source truly random? And and because those bits are from the previous data point, we're reusing the data from it. And okay, so this is kind of messed up, but yeah, but in practice, it's fine. That's what they said, that it didn't. But I don't think there really is a theoretical guarantee that it should be fine. But that is just that it is okay. Yeah. So the question is, how well does it work? And I believe these are the compression ratios, and this is the theoretical limit. 0.19 is the theoretical, and it reaches it, whereas the full MNIST, not the binary image, but the actual grayscale one, is pretty close to 1.39 versus 1.41. And this is also compared to using BB with pixel VAE against all the other image formats, and it's better than all of them. You can do better than that. I think these are all lossless images. Okay, and so this goes into the paper they wrote. Is that depends on the quality of the bound, the lower bound of the loss function. So if we have multiple latent layers, it apparently achieves elbow then with a single latent layer. I don't remember going through these multi-layer VAEs, but anyway, so we have latent variables which have their own latent variables, which have their own latent, or I'm sorry, I'm going the other way. So X, which has their own latent variable, I think it's multi-layer ones, or maybe it just means that yeah, the Z1 is based on Z2 and L-1 is based on L. So there's multiple layers for it. Can we use this for bits back coding? And BitSwap is their paper, and then they did the trick for it. They made it work for it, and yeah, and this is the paper, and yeah, it's the same idea as apply BB-ANS to recursively to these different layers of it, and each one is treated as a single layer, and then you build all these layers on top of it. Okay, and this is their algorithm. I think it's recursive. Okay, we'll just yeah, and this is their more details on their algorithm. And they have a trick on how to I think with recursive, it needs a fewer bits to get started, so you don't have to have a big amount of random bits to start off with. Yeah, it's yeah, I'm not quite clear on how these are done, but this was not covered in the lecture. But okay, so that was the basic idea of bits back. Do you have any questions or? Hopefully it was clear. I mean, somewhat clear on what the base idea of BitsBack is. Okay, I'll continue on. There isn't much left, but so the idea is how we used it with VAs. How can we do it with flows? So flow also gives us a distribution, probability distribution. So it should also be should be able to do it. Sorry, we have these density functions. So we cannot code continuous data. That's what flow is usually used for. So, but we have to discretize it to a high degree of precision. And then, yeah, there's still a problem is, I believe, just a general idea of the problem is that even if we with flows, even if we move a flow from X to Z, they're still all uh, Gaussian. It's somewhere here. They're still Gaussian, so it doesn't really help in coding. Here we go, compression with flows. Naive attempt is to use prior. This does not work well because if the flow is trained well, the distribution of the latents will match the prior, so there's no compression. So that there's no, because the number of parameters in X and Z are the same. So we don't get anything. We just move to another plane where it's still the same amount of complexity with flows. And so their idea is to turn this into VAEs, where you go into a smaller space. So basically turn a flow into a smaller space. And they have a technique for this where you where they scrunch up the space or something like that. So when they define it this way, then it becomes a VAE, and then it matches the variational bound um, um, to the first order. It matches it, and you can use bits back coding on this one. So basically, turning a flow into a VAE to make this possible. So, and they have other techniques. What so if you have the direct Jacobian, I believe, I'm not, so there's the Jacobian here. And so you have to directly factorize it, I believe. If it's high dimensional, it, like images, it doesn't make sense. And also the other solution is to do each layer at a time. And so you don't have to worry about the Jacobian. So they wrote a paper on this. So I didn't read that one. So this is kind of a little bit fuzzy on how the stuff works here. And yeah, I'm not sure. They talk about, well, it needs a lot of high precision data. How do we achieve it? And then you apply bits back to the extra position. And this is the variational dequantization bound. I'm not sure. They refer to it, but I forgot what this is. So I'm not sure how it works. But yeah, but they're saying like you can add some extra precision. Okay, and then this is the results for it. So theoretically, you're supposed to get 3.116, and their version of it, the authors here, got pretty close to it with there. So it wasn't causing a lot of, and CIFAR 10 emission, it wasn't causing a lot of a loss from going from of using flow models. And yeah, and this, I'm not sure how the auxiliary bit is the starting bit requirement was there. So I think it only works if you're gonna encode a huge amount of images, like an entire ImageNet set or something like that. So the first auxiliary is amortized over everything. Okay, yeah, this was for the flow model. There's a lot of it, but so I just skimming over it pretty quickly. So any things that we want to discuss on this? Okay, so I can move on. Oh, sorry,
is
go
there
ahead.
any comparison in a sense? I mean, do they tell you which of the two gives you better accuracy with lesser bits or any of that kind of stuff between the flow and the prior non-flow version?
I'm not sure. I can the CFAR 10 ImageNet. I don't know if they have any results here.
Because they compared or they gave results for just the basic stuff, right? Like how good it compared. And then I was just wondering whether the flow does anything, or is it just that, oh, let's just try and apply it, or is it really useful in any way that's practically relevant? other than, oh, it's a technique, so let's see what it gives us.
Oh, I don't know. It says ImageNet 64 by 64 3.66. Let's see. Image was 3.66. Yeah, so this is worse. I don't know why theoretical is higher than what they already achieved in the other one. So yeah, that needs to be.
It seems to be slightly worse, right? Even in the
Yeah.
best theoretical case.
Yeah. So yeah, for the others, the result isn't there. But yeah, they're converting it to a flow model, flow into a VAE. So maybe there's limitations there. Yeah, I don't know. Okay, so we can go to the last one, last part of it, Lempel-Ziff. I think this is a common compression algorithm, so it's not related to anything. But so just the general idea of the different types of statistical methods we can use for compression. So you have a static model where everybody knows the model, just have a model baked in, and it's the same model for everything. So Morse code, Huffman code, in that case. And dynamic model is generate model based on text and store the model also in the file. So the Huffman code where you read through the model. An adaptive model is learn and update the model as you go along. So LZW, the Lempel-Ziff, works that way. But decoding must start from the beginning, so you can't just decode from anywhere in the middle. Okay, so it does use this basic idea here is so we're in some position in the file. So we look through the preceding part of the file to find the longest match to the string starting at the current position. And so the idea here is this is the so we have suppose we're at this location right here, AAC. So we'll go and say, well, what is the longest sequence that I can find? AACA. Is there an AACA before that happened? There's an AACA that happened before. Then AACAB happened before. An AACAB happened before, and then you can see that this whole thing happened before, and you can just say, well, this has a look ahead buffer of size 4, so I guess you can't do more than 4. But yeah, it's just 1, 2, 3, 4. It'll look for AACA, and then it will say AACA or 3, 3, 4, B, 3, 1, 2, 3, 4, B. Okay, so it just sees AAC before, and it will just say, well, starting from position line 3, position, just use the one before from B. So we'll just copy, it will say AAC and then just say, well, just copy over from this part and put AAC here. And then, so example, when a dictionary of size 6 and a look ahead buffer of size 4, the current position is boxed, the dictionary is bold-faced, and the look ahead buffer is underlined. So the last step does not find the longest message outside of the window. So the window is only of size 6. So A will not see anything. So 0, 0A. This A will see 1, 1A. And this one will just say, go to position 1 of length 1. And then the next one is C. I think it's some sort of encoding here. Maybe I'm, yeah. Just go to 3 and have a length of 4, and that's the same. And then the next one is B. So basically, it's doing a look ahead. it's doing look ahead and see if you can find it somewhere. Obviously, this can grow exponentially in size depending on the dictionary size, the look ahead buffer size, the size of the file, all of that. And yeah, and then there's some idea on how well does this work. So if you have an ergodic source, that I think means that um, it it comes from a distribution, and it yeah, and it is not dependent on it's just dependent on this distribution only. So the integer t can be coded with log t bits because each symbol will reappear after some time. So on average, this is the formula for it. So there isn't a detailed workout of how this comes about. So, but it's just kind of put there. So that's probably given as exercise for the reader. But yeah. But yeah, that's essentially it. I've gone over a little bit quickly on some of these because some of them were not clear. And so yeah, they were saying there's a new encoder that you can alternative to bits back coding. There's a new way of also doing that, similar to what bits back decoding does. And this is the lossy version of it, um, lossy version of the problem. And there's something with convolutional ones. But yeah, that's all I have. If there's any questions, yeah, please, if we can have some discussions or anything that you want to comment on or discuss. I think the main idea is how this trick of using of achieving optimality by using the sampling as a source of information. And apart from that, it's just doing coding with a VAE or um, any deep model that produces probabilities. Yeah, if there's anything to discuss, or if not, then we can probably end early. Or yeah, this was the main topics here. And since they had two papers here, the bit swap and the flow models, um, I think they went into detail on this one. They didn't go into derivations of it, just a showing of the results. But this was the main part of it, was to be able to do encoding using on any model, any unsupervised learning model that produces probability, that you can use that for encoding and getting doing compression. And then this technique, the bits back coding technique, gives you the theoretical way of reaching the maximum, um, um, the the theoretical limit that's possible.
Does the encoder and the decoder that they use for the bits back coding have multiple layers, or
Oh, on BitSwap they have multiple
yeah?
layers. I think they make multiple layers of the VAE,
Hmm.
but in the normal one, I don't think there is. There's just one layer. Oh,
Okay.
this one has multiple layers, and they say it performs better. Where's the results here? I can't. Um, CFAR 10. I don't know what any of these, how they're coming up with these numbers. I don't know what the plus minus is. Yeah, and a number of parameters. So they have a oh, what's going on here? But yeah, the also depends on the size of the parameters they're training. So you have 45 million parameters, and so the encoder and the decoder must have that, both have the file. The program that encodes and decodes must have all of these parameters baked in, I guess.
So it doesn't seem like if the point or in the lecture do they touch on there's no is this an improvement on existing compression technique? Because it seems like, as you say, the level wave thing does or is most commonly used. So is it that these techniques, the bitback encoding, is better than the impulsive and gives you, or is it just that
Yeah, I think
these
this
are
one
techniques
shows.
with,
I think Lempelzef is used in GIF, isn't it? And GIF does better than, I mean, PNG does better than GIF. So I don't know if PNG uses, but it does better than all of these PNG BZ2 on binarized. But I don't know if how good PNG is on binary images. I think BZ is just not based on images, just the bzip command, right? The Unix command line. But it does better than all of them. But I think also the reason is you're transferring this big huge model, so it might have memorized parts of it, or yeah.
and also is it domain specific in the sense that text is better dealt with by some of the existing techniques, and as you say, in this case, there has to be, because I don't think in the lecture they do a macro level, here's what it's kind of applicable for, or, here's how it's different from what is done today in practice.
Yep.
Today.
No, I think it's whatever you train it on, it has to learn the distribution very well. So if it learns, the better it learns the distribution. I mean, and then I think also the better the latent space and all of that, the better compression you can get. But yeah, the other thing, yeah, so yeah, they don't, there is some comparison with the other techniques in the results section here. So this is the, so I think with the VAE training, there is a theoretical limit that you can calculate, I guess. And this only shows you the difference that you lose by using the coding. This is the minimum, probably the lower bound using the VAE, but it does pretty much, it does quite better than all of them. It's pretty close to BZ2. So I don't know what BZ2 is. I think it's, yeah, it's just the block sorting and Huffman coding. Yeah, it's a general file compression algorithm. It's not even specific to images. But yeah, it does much better when it's ImageNet, obviously. But this is all lossless image compression. And I think there was PNG, and now there's a huge push for the WebP that does better than PNG. but this does better than that. But it's probably very specific to, or maybe in the future we'll have image compression algorithms based on deep learning. And yeah, and all of these are lossless. And there's no comparison with JPEG and all of that. So even though we
a question.
Sorry, go ahead.
So how do we make sure that the compression is lossless? I mean, in terms of like practical implementation, can you like highlight this part, because I probably missed it.
Yeah, I was also a little bit confused about that. That how can you guarantee? I think it's let me see the algorithm here. So when you have the symbol S not, when you're encoding it, right here, when you're encoding it, you have to encode it fully with the bits. So the only thing that's continuous is the probability, but it only determines the size of the bits. So if you're wrong, or if your distribution is off, you have to pay more bits than that's necessary. But this S naught will always be discrete and will always be encoded. But the only loss that you could possibly get is because P is wrong, or P is rounding is not good.
Yeah, so they say they do it with VAE, right? And you somehow need to make sure that we do not lose the information when it's passed through VAE, right?
Yep. So here is the so also the encode with Z, right? So that's the part that gets tricky, because you could lose precision on Z. X is still discrete. X could be a symbol, but Z is something from the latent. And then they do say, well, yeah, we discretize at delta Z, and that part I was like, okay, but if you discretize it, how can you be sure? But they say the only thing is the KL divergence, so it just means you use more bits, but not that there's an error. I think that's the case. Wish they could have explained it a little bit more, but that part is like fuzzy to me. Also, is like here you encode Z with P of Z, but if the Z is not accurate, I guess it's still fine. The distribution is off, so you'll lose some bits at worst, but not the actual data, because the actual data is X. And so if you discretize it here, I think it doesn't matter. That's what I think. But and then the error is that it's just the KL divergence is the only thing, and that's the error in the bits. The size of the compression, not the actual result. But yes, it's still iffy because Z is continuous. You discretize it, and then you have a probability that's C. Then what happens? Yeah, it's a little iffy. Yeah, this all these parts about going from continuous to discrete, it really needs more analysis, and especially with flows and like the continuous parts. Yeah, these parts. Yeah, but from what they're saying, it should be fine. It is lossless, and then the errors are just with the compression lost, and not the data.
So another question. So we get this encoder and decoder through optimization, right? Given some data. Well, at least from those tables. And so the numbers in those tables would make sense only for the data that is distributed like CIFAR 10 or ImageNet or whatever. So is that correct? And like, I mean, about, so if you want to use this compression algorithm, you need to make sure somehow that your data is distributed in a similar way to the training data,
Yep.
right?
Yeah. So the compression depends heavily on the probabilities and the latent variables, how well you can represent it. If you can compress, if the latent variables can express a lot of the probabilities, are very confident in expressing them, then yeah, and you'll get much better compression. And
Okay, so
I believe
it would mean like if we want a more general like compressor, then we will have to sacrifice some of the compression rate, right?
probably, yeah, but probably would be interesting if like you have a dog specific compressor or compressor for outdoor scenes that does very well for outdoor scenes, or you can have a general one, maybe that it doesn't matter, that high level idea.
Yeah,
Is
just
it-
like in
isn't
the
it-
class conditioning, yeah, class conditioning and disentanglement based objectives in which you have certain objects or areas that are defined for a background scene or a particular object, and then they can compress much better. If we drill that down to suppose our uh, uh, then that can also be drilled down to a simple classification based objective as to recognize the particular class of a object those images have, and then try to decompress or compress it based on that particular class, and then they can be encoded to a latent space, and then those reverse operations can be performed.
Okay, that's a good idea. Yeah.
Mochen, but didn't
Yep.
you say towards the end, was that just for Lempel-Web that you said it's for any ergodic process, or is that for any of these?
Oh,
Can we
I
go back
think
to
it's
that
just for
slide? Is it just
I'm not-
Lempel-Web?
yeah, it's just ergodic just means that
Yeah, the distribution. I mean, I just checked, and it means that the
Okay.
distribution is guaranteed to probabilistically touch all the points rather than just a limited set of points.
okay.
So
I think
I was just wondering whether that's just for Lempel-Web or for any of these compression algorithms. That is, it's
yeah, that's yeah, I haven't thought about. I think for Lempel-Web, it's the ergodic part is just for to calculate these results, right? I looked it up also. Ergodic means that um, over time the distribution remains the same, that it doesn't change from one part to the other drastically. But with image, I think we're doing a very high dimensional, so each pixel is dependent on the one previous, so it's like a huge dimensional thing. So yeah, I'm not sure how big the history is, because with autoregressive you can have only look at the last 10 pixels or last so many pixels and things like that. So that also has the property that maybe it remembers that it doesn't need to be ergodic, that it will remember. But I think this is mostly for this this formula, with infinite streams. So with a long enough stream of data. But yeah, I don't know what happens if the distribution changes, or maybe I'm not. Just going to reasonable selection of points. Okay. Yeah, I haven't. There was no mention of this ergodic nature. Maybe it is implicitly there, or it's just mentioned here only. Yeah, I'm not sure. Yeah, yeah. Doesn't seem like Wikipedia has a short description of what it is. So I can't figure it out by just reading it. Yeah, and the other thing was that I think lossless images of ImageNet is not very useful because it's very low resolution, and then it's also you don't really need lossless there. So I think lossless would be good for like PNG, where it actually is a PNG, where it's like art or something like that, clip art or something like that. So that would be interesting how much difference it is, because PNG is not very good with that kind of compression, or other domains where it's not images, maybe audio or even text. That would be more interesting, I think. But there's no text, there's no audio results. It's all ImageNet, image-based. Yeah, as far as I can see, it's all image-based. Okay. Do you have any more questions, or do we want to end it earlier today?
Hey, no more questions. Thanks, Martin, and also just a comment. Thanks to everyone for staying with the course this year. I think this will be the last session for this calendar year, and we'll have the next 2 weeks as break because it falls on the day after Christmas, day after New Year. So we'll meet you all on January 9th when Arto will take us to the language, unsupervised learning in language, and then unsupervised learning in reinforcement systems or reinforcement learning, and that will then complete the course. So it's been a long journey. Hopefully it's been somewhat useful. And thank you all for joining. I think the next 2 weeks, as I said, will be a break, and we'll restart on the 9th of January, same time.
Thanks, Martin. See you, everyone.
Okay. See you, everyone. Yeah. Bye.
Have a nice
Merry
holidays.
Christmas, Happy New Year.
New Year.
Yeah,
Happy
Merry
New Year too.
Christmas and a Happy New Year too.
Okay. Okay. Bye.